Transformations can also be applied to mathematical functions. In this video, we're going to use the idea of translations and other transformations to show how easy it is to adjust the values you get from a function without actually having to know very much about the function in the first place. In doing this, we'll be able to generalize about the function and the features of graphs and apply those generalizations to other graphs and similar functions. This can make it easier to work out turning points or maxima and minima on different graphs. Let's have a look at what we mean by this by applying it to a simple graph of y is equal to x squared. So if we were to transform that function from y equals x squared to y equals x squared plus 2, what happens to the curve? Well, simply the curve moves up. And if we were to subtract 2 from the x squared, what would happen? Well, that's fairly obvious, isn't it? The curve would move down. So now let's think about the general function, y is equal to f of x. If we add a to a function, we're moving the curve up on the graph, and if we subtract a, we're moving the curve down on the graph. Let's make it a little bit more complicated. What happens if we have y equals x plus 2 all squared? What do you think is going to happen to the shape of the curve? Well, it shifts the curve to the left. If you look at that, when x is minus 2, y is equal to 0, and if you follow that through, you can see that all it's doing is shifting the curve to the left. Having seen that, it won't overly surprise you that if you do y is equal to x minus 2 all squared, it shifts the curve to the right. This in one sense is counterintuitive because adding a value is moving the curve backwards along the number line, and subtracting a number from the value of x inside the function is moving it in a positive direction along the number line. So let's just put that in generalized terms. Compared to the function y equals f of x, the function y is equal to f of x plus a moves the curve to the left, and the function y is equal to f of x minus a moves the curve to the right. Okay, let's get a little bit more complicated now. Let's look at y is equal to 2 times x squared. What happens here? Let's look at the shape of the curve. What's happened is that the curve has been moved up, stretched upwards. It's been pulled out upwards. And then we do that with the generalized function y is equal to b f of x. We're just saying that it's going to be stretched and made longer in a vertical direction. And finally, what happens if we look at y is equal to 2 times x all squared? Well, that curve is one that is squashed inwards. You would have to draw some points on there to see actually how that happens, the difference between the b being outside the x brackets and the b being inside the brackets. But where the multiplier is outside of the function, it stretches it vertically, and where it's inside the function, it squashes it horizontally. Let's look at how this can actually help us with a couple of real examples. So for any old line, y is equal to f of x, and we're just going to draw that there. Sketch the lines of y is equal to fx plus 4 and y is equal to f of x plus 2 inside the brackets. So first of all, f of x plus 4, if we're adding outside the brackets, that moves the curve up. Because there's a plus 4, it's moving the curve up. And then if we look at what happens with the y is equal to f of x plus 2, where the plus 2 is inside the brackets, it's a plus 2, so that moves the curve to the left down the number line. So the sort of question you might get asked is, if the minimum point of f of x is 1 minus 3, what is the minimum of f of x plus 4 in the first place? So all that's doing is moving the curve up by plus 4, so that's only going to affect the y coordinate. So the x coordinate is going to stay the same at 1, and the y coordinate is going to become minus 3 plus 4, which is 1. So the new minimum is 1, 1. Now let's have a look at what that means in terms of the y is equal to f of x plus 2 with the plus 2 inside the brackets. Well, that's moving the curve down along the x-axis. So our x-coordinate of the minimum point is going to decrease by 2. So it's going to go from 1 to minus 1. So the coordinates of the minimum for f of x plus 2, all inside the brackets, is going to be minus 1, minus 3. This is one of those bits of maths that actually looks quite difficult, because what is y of f of x? You know, what's the function? I don't know what that is. What function is it? Well, the point here is you don't need to know the function. And actually, if you can remember that adding a number outside the brackets moves the curve up, and adding it inside the brackets moves it to the left, and all of those different things, then this part of mathematics is actually quite simple. Don't overcomplicate it and don't overthink it. Just try and remember what those different transformations do in terms of moving the curve around, and once you've understood what they do in terms of moving the curve around, you can try and understand what they do in terms of moving individual points around on that curve. It's simpler than it looks. This process also works to help you transform some rather complex curves. The example here we have is of the curve y is equal to sine of x. That's a repeating curve that looks a bit like this. So if we have that curve drawn for us, we can ask the question, what does the curve of y is equal to sine of 2x look like? Well, we know that if we have a multiplied by 2 inside the brackets, that has the effect of squashing the curve closer together. So if it's 2 times, we can make the assumption, quite realistically, that we're going to get twice as much of that curve in the same amount of space. So we can see there that we've got the same shape, it's just squashed closer together, and there are twice as many peaks and troughs. Okay, let's see what that means now for y is equal to 2 times sine of 2x. That's effectively y is equal to 2 f of x, and we know that if we've got a 2 outside the brackets at the front of the f, that has the effect of stretching the curve along the y-axis vertically. So you can see, without even knowing an awful lot about the curve sine of x, we've been able to make some transformations because we've got those generalized changes that transformations make on functions of x. As I said before, this is an area of maths that looks to be more complicated than it actually is. As long as you learn the effects of the individual transformations on functions, you should find questions of this kind quite straightforward. Make sure that you are not confusing movements in the vertical or horizontal direction, and also make sure you're realizing that adding can sometimes move the function in the opposite direction to the one you might think of. Other than that, you'll find them quite straightforward.